So, hi everybody. I'm Markó from Center of Energy Research, and I will speak about neutron sources now. But before that, I have to say something about neutrons. So, neutron is an elemental particle. It is in the nuclei of atoms generally, and we have to free them. And then after freeing it, it will have very large energy. The free neutrons has a half time of roughly 15 minutes, and the mass of the free neutron is very close to the proton. It has no electric charge and it has a half spin, and the magnetic moment is connecting to it. That's a big advantage of the neutrons. So after freeing the neutrons, it has high energy, and we can see here the whole spectra of the neutrons from the relativistic one to the ultra cold one. Generally, the produced neutrons has the energy in this energy range. It's between GeV, MeV, and then we use the neutrons for scattering experiment in the hot, thermal, and cold range, so we have to cool them down. And for basic research, there are very cold and ultra cold neutrons, which can be also used, but it's really difficult to produce them. So how we produce the prompt neutrons? They are in the nuclei, so we need nuclear reactions to free them. We can do it with either with high energy particles, so bombarding with high energy particles, or we can use fission materials. And the as I said, it has very high energy, and we have to slow down them. And for slowing down, we use mostly scattering, and mostly on hydrogen or deuterium. There are many types of many kinds of moderators. I will show it during this presentation. And since we use these neutrons after moderator, we call the moderators a secondary source of neutrons. So that's why I will speak about the moderators as well. So from the very low intensity to the higher intensity, there are the handy sources. It's alpha decaying isotope and beryllium. Mostly it's polonium, plutonium, or americium, beryllium sources, where the alpha particle reacts with the nucleus of beryllium, and the beryllium will emit neutrons. They can be used for looking at moisture or checking neutron detectors, and there are some other industrial application. There are also small accelerator-based sources. They are working with deuterium-deuterium or deuterium-tritium reaction. They produce very high energy neutrons, and they are used mostly for investigation of nuclear reactions. There are small accelerator-based sources. They use mostly protons to excite beryllium or lithium, and in the same way as the handy sources, the beryllium or lithium emits neutrons, and they can be used as a compact neutron source for neutron scattering. In the future, I think it will be the large part of the neutron sources. And the bigger neutron sources are nuclear reactors and spallation sources. They are large accelerator-based sources. And in the future, maybe fusion reactors will work also as a neutron source. The problem is there are two problems that at the moment they don't work. They don't produce so much neutrons, and on the other hand, the produced neutron has extremely high energy. It's really difficult to moderate them. So let's go through the bigger sources. The nuclear fission uses mostly uranium, sometimes plutonium. When slow neutrons arrive to the uranium-235, and fission happens, so the nucleus became two smaller one or three smaller one, and emits in average 3 neutrons. From these 3 neutrons, one will be used for other fission, and the 2 other can be used for other purposes, for example, neutron scattering. And the intensity of the nuclear reactors are depending on the power of the reactor and also the geometry of the active zone, and the limiting the bottleneck is the heat removal. So we can not remove infinite amount of heat from the reactor, and that limits the neutron intensity as well. So generally they use uranium, highly enriched uranium, not like in the power plants. The moderators are water and or heavy water, and the moderator is also the cooling medium, which cools the reactor. There are sometimes reflectors, or sometimes beryllium or water. I will show some example. And we have horizontal and vertical channels for experiments, either irradiation or scattering experiments, and they mostly work in continuous mode. So here there are 2 examples. The biggest reactor-based neutron source is the ILL in Grenoble in France, and it has a very compact source, and around there is a D2O tank, and it has a very high enrichment uranium, and the neutron flux at the core is 1.5 times 10 to the 15, while our reactor is the Budapest research reactor. It uses lower enrichment. It's 18% enrichment uranium. We have simple water moderator and beryllium reflector, and the neutron flux at the core is 2 times 10 to 14. It's because the geometry of the active core is completely different. This reactor is not designed primarily for neutron scattering. Meanwhile, ILL is designed just for neutron scattering experiments. Here we can see our campus. Here is the chimney of the reactor, and in the reactor hall here you can see our 10 megawatt reactor. And it's just a picture how what we can do with these neutrons. Here are the active cores, and we have 15 instruments around the reactor using cold neutrons here and thermal neutrons as well. We'll speak about later. And there is one special reactor which is used for neutron scattering. It's in Dubna in Russia. This is the IBR-2. It's a fast reactor using plutonium and sodium cooling. And in the middle here we have the active core, and there are reflectors which reflect the neutrons, 2 of them, and they are rotating. And when both of them is in front of the active core, then this reactor will be highly supercritical. Supercritical means that the generations after each other, generation of neutrons, has more and more neutron. The critical reactor is a normal working where the power is average in the average, and it works continuously. In our case, it makes a very high power, where we can see it's gigawatt, and then goes down to 0, close to the 0, and that's why in the peak there is a missing here, is 10 to the 16 neutron per second per square centimeter in the peak. And we can use it for time of flight experiments. In the afternoon, I will tell you what is time of flight measurement. The other types of big sources are the spallation sources. During the spallation, a very high energy protons are hitting high mass nuclei, and with this high energy, there is a so-called evaporation before the nucleus fall apart to many small other nuclei. And during this reaction, we get 30 neutron per reaction. So at first look, it's much better than fission reactors. Of course, neutron intensity depends also on proton energy, proton intensity. But the bottleneck here is also the heat removal and the cavitation in the target. So we have a high intensity pulse coming into the target. It makes a plasma, it cools down, and finally it can the cavitation after cooling down can break the target to small pieces. So that's the main bottleneck of having high intensity. Right, so two spallation sources. One, the ESS will be built in Lund. It's actually under building. Now the target is on their place. It will be the highest intensity neutron source in the world when it will be built maybe in 23. And SNS in Oak Ridge, that's a working spallation source for 20 years. And they have a little bit differences. The target of ESS is tungsten. Here it's liquid mercury. The proton, they both use photons, but the SNS SNS in the accelerator use hydrogen negative ion. I will tell you why. And they have roughly the same energy, proton energy. What can be used in general, it's from some 100 MeV to 2 GeV proton energy, which is important that this 2 GeV is highly relativistic. So the proton at 1 GeV has a double mass comparing to the rest mass of the proton. And which is very important, that the primary neutron can have almost the total energy of the incoming proton, which means that we can have some GeV or some 100 MeV and GeV neutrons, and it's really difficult to shield against them. And there is also an exception. They are working in pulsed mode because it's much more efficient, except SynQ at PSI. It's a Swiss intense neutron quelle. That's a SynQ, which is a continuous spallation source, and it has roughly the intensity very close to our reactor at Budapest. So what's the difference between the two spallation source I mentioned? That SNS and actually all of the other spallation sources use short pulse. Why short pulse is good? Because we can monochromatize the neutrons by measuring the flight time, and if the initial pulse is very short, then we have very high resolution. The problem is that for making short pulse, we need an extra condenser ring here, and then feed it into the target. So it's a little bit expensive. Then Ferenc Mezei proposed the long path source, which doesn't have this condenser ring. This is the ESS. It has a linear accelerator directly sending protons to the target, and it gives higher intensity. It needs a much more simple accelerator, but for that we need very long instruments. At the ESS, the long instruments will be 160 meters long. And here we can see the shape of the long path used at the ESS. We can chop it by using neutron choppers, and we can make shorter paths. And as a comparison, here we can see the response of the moderator at the SNS. As we can see, at the same instantaneous path intensity, the intensity is much higher, because we don't see only the peak, we see the integral of this response function all over this 3 millisecondum. So how we moderate the neutrons? So the best way is for moderation is playing a billiard, meaning that neutron goes into the medium, and after scattering it loses the energy. The best moderators are hydrogen and deuterium, because they have the mass very close to the neutron. So actually hydrogen has almost the same mass as the neutrons, but it can have it has a bit higher absorption than deuterium. For thermal neutrons, the best way for moderator is using water or heavy water, and in compact source they use paraffin because it's easier. And sometimes we need a hot moderator, and the hot moderator is graphite. It's because it's really hot, it has high temperature, it's much more safe than using hydrogen or water, and the carbon also has high cross-section. So here we can see two examples for moderator. This is the reactor core of FRM2 in Munich. Water is the moderator around a very compact core, and in spallation source the target cannot be put into the water. So above and below the target there are water and liquid hydrogen moderators, which cool down the neutrons, and then you can lead them out to the instrument. So the cold moderators needs really a cool medium, and it's generally 20 Kelvin cold liquid hydrogen or deuterium. And it has some strange parameters. The hydrogen has two spin states, the ortho and para, and the spins are parallel or anti-parallel, and there is a 14 milli-electron volt energy difference between the two states, and the transition is almost totally forbidden. So here we can see the cross-section of the hydrogen as a function of neutron energy, and because the 75% of the scattering on hydrogen happens with spin flip, then the parahydrogen cross-section decreases very sharply at around 14 milli-electron volt, because the neutron cannot flip the spin at a parahydrogen, and we can use it because if a neutron comes into the moderator, it will lose its energy also by scattering and by changing the state from ortho to para, and it can go out without any additional scattering if we have parahydrogen in the cell. So it cools down and then lets out the neutrons in this direction. Sorry, there are the guides. Meanwhile, orthohydrogen can thermalize the neutrons, but then when neutrons are in the middle, they cannot come out because there is another reflection. So the goal of the cold source is to use parahydrogen next to the active zone. For time of flight measurements for pulsed reactors or pulsed sources, there are many kind of different slower and faster moderators. They are general moderators, but sometimes we use extra shielding, mostly cadmium or gadolinium, around the hot source, which produces very sharp peak but much lower intensity. There is the poisoned moderator. Poisoned means that around the cold source there is the water, and there are neutron absorbers in the water. So only the fast neutron can be thermalized by the cold source. And the neutron will not scatter forward and back before it could go out. And the decoupled moderator is a simple cold source wrapped in gadolinium, and this is much more. This gives much faster pulse shape, and we can see the intensity also goes down. With this kind of source, we can reach some microsecondum pulse shape or some tenths of microsecondum if we are going to lower energy. And there is a new direction in the moderators. It is the so-called low-dimensional moderators. It comes from Ferenc Mezei. Here we can see a large volume moderator filled with hydrogen. The outcoming intensity can be seen here. Below there is the target, and the fast neutrons come from below, and at the surface we see hydrogen. Above there is a reflector, so at the top surface there is some neutrons coming out, but in the middle it's much lower. So if we decrease the height of this moderator, then sooner or later we will have only surface, only the skin effect. And this is the ESS moderator, is 3 centimeter high, and it has much higher brilliance or much higher flux at the surface. Here we can see this half of this moderator, the liquid hydrogen is in this aluminum, and it has 3 centimeter height, and it produces 3 times higher flux of neutrons in this area than the volume moderator. The total number of neutrons are higher here, but what the instruments need is mostly the flux of neutrons, not the total number. And finally, let's see what is the status now in Europe about neutron sources. There were many, but slower they die out. So at first, HMI Berlin, which has the same power as the Budapest reactor, was closed, and then Schieler, that's in Norway, that's a smaller one, and then in Saclay the Orphée reactor was closed as well, and the remaining, oh, the arrow is missing here. Here is ILL Grenoble. Hopefully it will work till some 10 years. And there are smaller sources like in Delft in Netherlands, and Rzeszów, Prague, and in Greece. close to the ILR source, there is a highly intense source, the FRM2, and PSI and ISIS are the spallation sources, and our reactor is still working. So the future of the sources is not so bright, because in Europe nobody will build new reactor sources. The high spallation sources are highly expensive, but we need smaller sources. On one hand, because the efficiency of the large sources for short measurement is very low. So one has to change the sample, one has to change the sample environment, and so on and so on. This takes time, and changing the sample and sample environment during half an hour and making 2-second measurement, that's not so efficient. So we need a smaller source for easier measurement, and reactors will be closed sooner or later. So what's the solution? The solution is the compact neutron sources. Compact neutron sources are working with lower energy proton accelerator, where lithium or beryllium is irradiated with this proton in between 10 and 100 mega electron volt energy, and they produce moderate intensity of neutrons. So they are not so high intensity sources, but much more much less intensive than a reactor or a spallation source. So a smaller compact neutron source can be built in the future at different universities, and they can go there to their own source and make preliminary measurements on their own samples. There are some projects about building this kind of compact neutron sources. One compact neutron source is actually under building. It's in Hungary. It's our research center, and the Neutron company builds a very small one. It will use lithium, most probably. And there are planned other sources in Saclay, in Jülich and Bilbao. They are going to build compact neutron sources with the same neutron intensity as medium-sized reactors like in HMI or Budapest Research Reactor. And the compact source, it looks like this one. Since the source is very compact, then you can make many smaller source, optimize it for a given instrument type, and with one accelerator you can feed many different instruments. But since you have many sources, each of them can be highly optimized for a given instrument type. Even if the intensity is lower than at a reactor or at a spallation source, due to the higher efficiency, they will be also useful for making very good science with neutrons. And that's the end, and thank you for attention.